easier to catch it later on. So we are recording the program now. Welcome to another in this series of talks from the CAA. Paul Fellows, the chairman, has done all the talks up to now. So tonight you have the pleasure of me, and we'll see how it all goes. The talk is one I've given before to the Papworth Astronomy group, and it's about an hour-long talk. The plan is to break it in the middle, just for let people have a quick stretch of the legs, grab a cup of tea or something like that. So we'll do that. And then the other thing which I thought might be quite interesting for people to know is you may be aware that today is the 50th anniversary of the Apollo 13 setting the record for the highest absolute altitude attained by a crewed spacecraft. I don't think it was a record they really wanted to have, but they attained the altitude of 400,171 kilometers from the Earth. So that was a pretty amazing thing as they went round the back of the moon. I'm just muting the other microphones, I think. I'll try to, because I had to do them individually. I'll just do a quick bit of muting. Try to. It's gone quiet anyway, but for some reason I'm not able to mute everybody. I'll try. It's because people move around on my screen. Right, that's better. I think we've got there now. And somebody's trying to send me a message, Amy Woodhall, but I don't think it's coming through, so I'll get rid of that as well. And we'll try and carry on. So as I say, it's the 50th anniversary today. It was at 1921 Eastern Standard Time, so that'll be in about 5 hours' time will be the point when Apollo 13 disappeared around the back of the moon. And for any of us who are old enough, remember the tension as the spacecraft went around the back of the moon, knowing they had to do a burn on the back of the moon in order to reset their trajectory to get back to Earth. So the Cliff Mitchell Moore and the Patrick Moore on TV telling us what was going on was quite amazing. Anyway, the purpose of this talk, it's quite light-hearted talk. The idea is that I'm going to go through the solar system. We're going to start at Mercury and work our way right out to the edge of the solar system. I'm going to try and introduce a few interesting facts which you may not know. The facts I'm going to go through, and get my screen to flick over to the next slide, are first of all something about Mercury and something about Mercury's core. So you have a little ponder on that while I wrote through the rest of the questions. We're going to talk about Venus and some of the fascinating elements about Venus. The perpetual question of what is the moon made of? So you can come up with your answers for that now, but we'll see what we get to when we get to that section. We'll then have a quick break, and then we'll move out to Mars and talk about Phobos and Deimos, and I'll introduce you to some interesting facts there. People who've seen Paul Fellows talk about Mars will probably know the answer to this one already, but hopefully it'll be news to some people. Fifth question is a factor which not everybody knows that all the giant planets have in common. So we'll go through that as we go to the outer solar system. And then finally, a total tally of the number of moons in the solar system. And even though I only gave the talk to the Papworth Astronomy group about, I don't know, 6 months ago, I've had to update the numbers. So this is, it's news to me as well for this one. So those are the 6 things we're going to try and capture. I'll come back. Oh, hello. Who is that? No, I'll carry on. Okay, so let's have a look at the overall situation. So this is a very busy chart. Don't worry if you can't see all the detail. It's actually about 3 years old, and it's all of the space flights which were planned from 2017. So down at the bottom, you can see the list. I think I'm going to have to go. I'm just going to do some more muting. We've got some more people up now.
Charles is Edmund's son, and the rest will follow.
I'm just going to mute the newcomers. Excuse me, bear with me a second.
Jonathan, it's Paul. What you need to do is.
Oh, I just muted you, Paul. Sorry. I have tried the mute all button and it isn't working for me for some reason. But we are now muted, so we'll carry on. Right. Yeah. So the lower picture here is the total solar system. And it's showing you some of the missions out to the farther reaches, such as Juno and Cassini. And And then there's a blowout of this central area up here, which is the inner solar system. And this is showing you the missions which are happening within the boundaries of Mars and inwards. And then even further blowouts, you have the Mars missions, which are shown over here, and the Earth missions, which are shown over there. And what I'm striking, I'm not going to go through all of these missions, but it just strikes me that so much is going on at the moment. There are so many missions going out to get us more and more information. It's not at all surprising that every time we do a talk of anything about the solar system, we find out that we have to update the talk with new data, which is, I just find fascinating as we go on through. So lots is going on there. And if we look at the 2021 onwards area, you'll see that we have a whole load of launches of to Mars, out to Jupiter, out to Psyche and some of the other planets, and inwards towards Mercury. Let me just once again see if I can do a mute. I'm going to find Paul because he might have some useful information about how to unmute or mute people in general. Paul, you're back on.
Yeah. So what you need to do is go to the icon.
Oh, sorry, and I've muted you again. It just jumps around all over the place. Right, I've unmuted you and I'll leave you unmuted, Paul. Just could you repeat that, please?
Okay, so the appearing and disappearing icon bar at the bottom of your Zoom screen has a Manage Participants button.
Right.
If you open that, you'll get a list of everybody, like in a panel at the side.
Yeah.
At the bottom of there are some buttons, one of which says Mute All.
Yeah. And
Click
that was the
on
one
that.
I keep hitting it and nothing much happens. But
You should then get a dialog box that comes up, and you have to answer the question very carefully, which is yes. Even though it looks like you want to answer no.
Okay. I'll probably have to jump out of screen show to do that. I don't see the dialog box. So what I'll do is I'll carry on and
that'll be it.
I'll just mute the ones which I've got I can see now. I'll leave you unmuted, Paul.
I shall try not to snore then.
Right. And I'm just having a quick shufty. I think that's got everybody. Yeah, there's people drifting in, unfortunately, so we're getting a few more people as they come in. There was a dialog box. Actually, let me just get out of this for a second. I'm going to stop the sharing for a second. That's the dialog box. Okay. Right. That was the problem. It was because I was on a screen show. So if I now go back to sharing screen, back to that. Okay, right. Everybody should now be muted, and I physically have to unmute them, but I think people can unmute themselves as well. So we'll carry on. So that was just a quick view of what's happening in exploring the solar system at the moment. We'll now move on to talk about individual planets. So we start off with Mercury. And the first thing we see with Mercury, apart from listening to a bit of the Planet Suite, is that we have Mercury being the smallest and closest planet to the Sun and looking remarkably like the Moon. You can see all of the cratered surface here. And this is because it is, in many ways, has gone through the same sort of evolution as the Moon. There's no atmosphere to speak of, and therefore it's been battered and smashed by meteorite impacts over time. And there's been no recent volcanic eruptions or activity which has allowed the surface to be resurfaced. So you can see that there's masses and masses of craters across the surface there caused by impact craters. The other interesting things about Mercury is up in the northern hemisphere up here, we have areas which exist in perpetual shadow. So even though it's a planet which is the nearest to the Sun, therefore you'd expect it to be very hot, there is some perpetual shadow. And as there's no atmosphere, that just gets very, very cold. And in fact, we have now got information from the Messenger probe in 2012, which confirms that there is actually ice, water ice and organic other ice in the craters at the North Pole of Mercury, which is quite amazing. So we have the nearest planet to the Sun, but we have ice at the poles, which is not really expected. Few facts about it. We've got an orbit of 88 days, and we have a rotation of 58 days. So actually, it only spins round 3 times for every 2 orbits it does, which causes havoc with your birthday calendar. One of the things which wasn't really expected when we were doing missions to Mercury was that there would be a magnetic field. And in fact, there has been discovered a magnetic field. It was actually picked up by Mariner 10 in 1974. It's very weak relative to the magnetic field of the Earth. It's about 1% of the field. And it is caused in the same way by a dynamo effect inside the planet. And the reason we didn't think there'd be much of a magnetic field was because the planet is spinning so slowly. If you think about it, the Earth spins every 24 hours, and so things are moving fairly quickly. And we've just said that Mercury only spins once every 54 days. So it's a much, much slower rate of spin, and it's a much smaller planet. However, there is a magnetic field. And you can see here that the magnetic field, there's two elements here. There's the graphic in the background showing how the waves of the magnetic field are aligned, much the same as you'd have had with a school bar magnet experiment. But then we also have the strength of the magnetic field as you go from in front of the planet. This is the sun, will be on this side over here, moving through the planet, the strongest part of the magnetic field here, and then fading away again as it goes beyond the planet. And that's enough of a magnetic field to actually create a bit of a shield for Mercury. But there's nothing much to shield against anymore, but that's what it's for. So there's a bit of a mystery. How does it have such a strong magnetic field? And the answer is it has a rather immense iron core at the center. So this is a cutaway view of Mercury. And you can see that we've got a crust, the same as we have at Earth, and we have a mantle. The core is a huge iron core in the center, and it's got an 1,800 kilometer radius. And this is in comparison to the Earth's core, which is only about 1,200 kilometers. So Mercury, although it's a much, much smaller planet, has a much larger iron core. And in fact, the iron core in Mercury has more iron in it than any other planet in the solar system. So a very strange thing. So how have we ended up with a planet which has got such a large iron core, although it's a very small planet? So that's one of the questions. And if we go to a view of the outside of the planet again, and we look at this impact area on the side of Mercury called the Caloris Basin. So it's shown here, it's in false color. You can see this large brownish area here, which is 1,500 kilometers across. And when you think about that in terms of relative to the size of the planet itself has a radius of only 2,400 kilometers. So it's as if you have an impact basin the same size as the Pacific Ocean on the Earth. It's massive. And in fact, you can look at the size of it. You can't see it here, but there's on the edge of the basin, there is a ring of mountains, which is about 2 kilometers high. And then there's also rings going around. This blue area, this is another area which is part of this impact. So something very, very large has hit Mercury at some point in the past. And there's even some evidence that there's the rebound mark on the far side of the planet, but I don't have a picture of that at the moment. So we have a very, very large impact crater. So what caused that? Well, I think something very large, maybe 100 kilometers across, collided with Mercury very early in the evolution of the solar system. So we've been, broadly speaking, the solar system is about 4.5 billion years old. And in the first billion years of the evolution of the solar system, there was a period of bombardment when there was lots and lots of collisions caused by comets and various asteroids and rocks all shooting around, being deflected out of wherever they came from by the orbits of the large planets which were being formed. It was chaos. So things were hitting each other and there was lots and lots of damage being caused. We think this would probably happened towards the end of that period, because if you look at the Caloris Basin, if you go back one slide, you'll see that there's actually not that many craters in the basin itself. It's relatively smooth in the center. It's a little bit like some of the mares, the seas on the moon, which have got a smoother layer because they've been flooded by the volcanic outpouring after the impact. And we believe much the same sort of thing has happened with the Caloris Basin. And a very large impact caused this big crater. There was a volcanic outpouring from inside the planet which caused the smooth area inside it. And the impact was so large that it probably took away a whole load of the outside of the planet. The planet could have been much larger, but what was left behind was the iron core and a very relatively small layer of the rest of the planet to continue to exist, which is why we end up with a very small planet, but with a very large core. So it's an unusual place. So that's all I've got to say about Mercury for the moment, but it's an interesting snapshot of what's happening on Mercury. Oh, I'm sorry, one last thing on Mercury, I forgot about this slide, is how can you see Mercury? You can see it in a number of ways. It does rises and sets along with the sun. It's obviously in the direction of the sun, so you can see, you can observe it through a telescope. You can occasionally see it with the naked eye, but it's very, very small, and it's also quite a dangerous observing target because you're pointing your telescope fairly close to the sun, so you have to be very, very careful in what you're doing with it. And then a couple of times a year there is an opportunity, and it only happens at around November and May, which is when the inclination of Mercury's orbit coincides with the inclination of Earth's orbit, when you might be able to see Mercury passing in front of the sun. But this doesn't happen every year. And for those of you who were with us in November last year, you remember we actually had a successful Mercury transit observing party up at the Institute of Astronomy. And we're able to see Mercury passing in front of the sun through our telescopes, which was great. And I'm really pleased we did that, because the next opportunity isn't until 2032. Hopefully we'll be out of lockdown by then, but it's a long way in the future. So we'll now move on, and the next stop is Venus as we move out across the solar system. Earth's evil twin. It is about the same size as Earth, but it is closer to the sun. So it's possibly still in the Goldilocks zone, as they call it, in terms of being a potential area for habitability, because you can get water appearing in all three of its forms. However, it is closer to the sun, and it's therefore had a lot more heat. And this picture is a fairly typical picture of Venus. It shows you that it's covered in dense clouds, so it's very hard to tell what's going on below the clouds. And then the other thing about the orbit of Venus is that it has a very, very slow rotation. So one Venus day is about 115 Earth days. And it orbits in 224 days. So basically you have 2 days a year. So you have a lot of birthdays, birthday every other day. It's difficult to photograph. I put this up simply to show how difficult I find it to photograph. I think we have a better photograph later on in the sequence. This was one I took about 4 or 5 days ago through a standard compact camera, so not even using a telescope. And I was struggling to get the exposure right. So it's rather overexposed, but it just about shows you that you've got a disk of some description with a little bit of phase space on it. This is a view of Venus through the clouds taken with radar. So this now lets us see what's happening on the planet itself. You see that there is quite a lot of marking on there. But if you think back to the picture of Mercury with all of the craters, this is a very different landscape. You've got some areas which are very smooth. You've got some areas which are sort of mountainous and volcanic. And it demonstrates that there's actually been activity on Venus in the more recent geological past, and therefore any impact craters which might have happened have been minimized by the activity of the volcanic activity on the planet. Various different research and analysis has shown that there is quite significant volcanic activity on there, and there are a number of different areas. There are things called fara, which are flat-topped volcanic features. There are radial star-like fracture systems called novae. There are features with both radial and concentric fractures, which are looking like spiders' webs and known as arachnoids. And I'm wondering whether this is one of those down here. And then there are coronae, circular rings of fractures, sometimes surrounded by depressions. So quite a few different features, all of which are volcanic. So we have a lot of activity on the planet. And when you get down actually onto the surface, you get a picture like this. Now, this picture has been taken as a radar picture from the Magellan surveying satellite spacecraft. And it's a mountain or a volcano called Mart Mons. And it's 8 kilometers high. Now, this picture is slightly skewed. It's actually been stretched to actually illustrate the geometric features and geologic features a bit more. But what you can clearly see is this slumped volcano here, and you can see some relatively recent lava flows here, which is once again demonstrating the volcanic nature of Venus. But one of the most extreme features of Venus is the atmosphere. And the reason you can't see the surface is because of the cloud layer. Let me explain this graph to you. On the left-hand side, we have the altitude. We start at 0 ground level, go up to 50 kilometers, 100 kilometers, 150 kilometers. On the right-hand side, we have the pressure, the atmospheric pressure on the planet. And the atmospheric pressure is caused by a combination of the amount of gas in the atmosphere and the gravity of the planet. Now, on Earth, we have one atmosphere at sea level, so that's at 0 kilometers. But on Venus, because of the weight of all of that gas, the one atmosphere point actually occurs around about 50 kilometers up. So that's where we have our parallel. And also at that point, the temperature is here. And if you take that temperature around about that point here, around about here, and drive down to the temperature scale, you'll see it gets to 300. And that temperature scale is in degrees Kelvin. Kelvin is the absolute zero-based temperature scale, starts at minus 273 degrees centigrade, which is absolute zeros when everything stops moving. So a temperature of 300 Kelvin, which is this one, is 27 degrees centigrade. So very similar, if you like, to the position on Earth. So the only problem is you have to be 50 kilometers in the sky to achieve that on Venus. As you carry on down towards the surface, the pressure rises to something like 90 atmospheres, 93 bar at the surface, and the temperature rises to 467 degrees centigrade. So it's very, very hot and very, very unpleasant. And just as a sort of a comparison, the Seawolf class nuclear submarine, which is one of the most advanced nuclear class submarines, has a maximum depth of 50 bar, that's 500 meters. So if you took one of those onto Venus and put it on the planet's surface, it would probably get squashed. Which is just some illustration, which also means it's very, very difficult to land a spacecraft on Venus to do any further work. However, it has been done. I'll come to some pictures of that in a second. Just wanted to finally show you, illustrate why it gets so hot on Venus and why it makes Venus the hottest planet in the solar system. And you compare the two situations of Earth and Venus. On Earth, you're familiar with the idea that we have a greenhouse effect, and that's caused as we build up more ozone or more things like carbon dioxide in the atmosphere, which means that when the sunlight comes in from the sun, it hits the surface, it heats the surface, and then it bounces off, and it then tries to escape. But if there's a layer of carbon dioxide or other greenhouse gases, it can't bounce off, and it comes back down again, and it's reabsorbed infrared radiation. At the moment on Earth, we are gradually making this worse. However, at the moment, it isn't extreme. On Venus, it's gone the whole way. And we have this situation where the incoming sunlight, it has more incoming sunlight, obviously, because it's nearer to the sun. Some of it is reflected away by that layer of clouds, but the sunlight that gets through is able to heat the ground underneath it. And that then bounces off to try to get re-radiated, but it can't. It gets stopped by the cloud layer, by the greenhouse gases, and then it gets thrown back down to the ground and carries on the heating cycle. So it's this vicious cycle of continuous heating, which has caused the temperatures on Venus to go so high. And I promised you images from the surface. This one is actually one of the few color images from the surface. There have been a number of Venus landers. They're mostly Soviets, in fact all Soviet, I think, and this is from Venera 13. I think the first mission to land on Venus was Venera 11. I may be wrong about that, but that took some black and white photographs. But this shows you what you see as a tourist on Venus when you've landed for your holidays. This spacecraft was designed to last for 2 hours. No, sorry, half an hour, but it actually survived for 2 hours. And it landed in March 1982. And nothing has gone back to Venus since the 80s. And it's a planet which we could probably deserve to do a little bit more research on. However, given the heat and the unpleasant nature of the surface and the pressures, it's probably not a place which is going to be studied very much. And a lot of the focus at the moment is on other places where there may be potentially sources of life or evidence of past life, which people are very interested in looking at. To make things worse, we've got very, very hot, very, very high pressures. There is rain on Venus, but it's made of battery acid, it's sulfuric acid, and it's falling continuously, but it never reaches the ground because it's so hot. It just gets evaporated and cycles back around again. So you have the equivalent of a water cycle, but with acid, which is great. And you might even get snow. So high on the hills, there is something which looks like snow, and the analysis of that suggests that it's composed of both lead and bismuth sulfides. So we've got sulfuric acid rain, we've got lead-based snow. It's probably not the place you want to choose for your winter holidays, is it? And then finally, I promise you a better picture. I think this might be one of Paul's, actually, from a previous presentation. It shows you that you can image Venus. It is very bright in the sky. And in fact, at the moment, it has been very bright for the last few weeks. It's definitely worth having a look at. And you can impress your friends by pointing out that that very bright star over there isn't a star, it's actually Venus. And as it moves around and as its position in its orbit changes relative to us, you can quite clearly get to see that you get the phases of Venus. I wasn't able to demonstrate that in the photograph I took a few days ago, but this picture clearly shows a position where there's only a part of Venus is visible because the rest of it is in darkness because it's not being illuminated by the sun. So that's enough about Venus, a very hot, very high pressure place. We'll now move on a little bit closer to home. This is our inner solar system picture. And so you can see we've got Mercury visited already. There's Venus and Earth. And you can see there's very similar sizes between Venus and Earth. We're now going to come to Earth, but we're not going to look at the Earth too much. This is Mars over here, which we're going to come to later. But first of all, we're going to come towards the Earth and have a look at the Moon. So this is a very nausea-inducing animation, so I apologize for this. The reason I wanted to show you this is for a couple of things. One is to just illustrate that although everybody, I think, knows that the Moon is tidally locked to Earth, which means we always see the same side of the Moon. And this is showing you the side we see. You can quite clearly see the area of the Sea of Tranquility where Apollo 11 landed up here. But you can see it's wobbling. And this is what happens as the Moon goes around its orbit around us. It's also getting larger and smaller, and that's because the Moon's orbit is not absolutely circular. And you may be aware that the full moon we had about a week ago was a supermoon, and a supermoon occurs when you have a full moon when the Moon is at its closest to us, and it's one of the larger phases of the Moon. A supermoon or a large moon like that is what you also need for a total solar eclipse, because it's only when it's the closer to us and therefore bigger that it can fully cover the face of the sun in a solar eclipse. If it's in a smaller place, when it's further away, you end up with what they call an annular eclipse, where the edge of the sun could be seen all the way around the Moon. The other thing about this image is you get this wobble, which means that you don't always see exactly the same 50% of the Moon. You can actually see 59% of the Moon because it wobbles a little bit around. And this is through a process called libration. And it means that if you go to a pub quiz to say how much of the Moon can you see, you can say, I can see 59%, and you should win the prize if the quizmaster knows his stuff. Now, big question is, why do we have a Moon like this, and how did it get there? There's a few clues as we look at some of the data over here. It's about a quarter of the diameter of the Earth, and therefore if you do the cube of the quarter, you end up with a 1/64, which tells you it's 1/64 of the volume of the Earth. But when we calculate the mass of it, as you can do through some of the gravity measuring experiments that have been done, we find out it's only 1/80th of the mass of the Earth. So it's lighter than we would expect it to be. So the question is, well, where did it come from? Maybe it was grabbed by gravity. Maybe it was a passing rock which happened to wander too close to Earth and got caught in our orbit. Maybe it was formed along with the Earth. I mean, when there was the solar system was being generated and there was a great big disk of material around the sun, maybe the two formed together. Or maybe it was actually part of the Earth and got split off. And these are the three hypotheses which have been mulled over the years. And we'll just go through a little bit about how do we now have a conclusion on all of this. So when the moon landings happened, so 50 years ago, it was the first opportunity to be sure of getting some samples from the moon. There are some moon meteorite rocks on the Earth which have landed anyway through various different means, but this was the point where we actually brought back samples which we could absolutely say have come from the moon. And we also sent up a space dog who's burrowing away down here to get us out some more material. No, we didn't. It's just a nice graphic. The question was, what did we find when we looked at the space rocks from the Apollo missions, which was brought back? What we found was the moon is made of Earth stuff. So we found that the composition of the rocks on the moon was the same as the rocks on the Earth, but it was only from the rocks of the crust and the mantle, the outer parts. What we didn't see was much metal and almost no heavy iron core. Now, obviously, we couldn't drill down to the center of the moon. However, you do get traces of iron in the mantle on Earth, and we would have expected to see traces of iron in the mantle on the moon as well, in the crust, as what I would say. So we didn't find those things, but we did find this material from the Earth's crust. So what does that mean then? Where does that take us? Well, it didn't come from afar. If it had been a rock which had been captured as it flew past the Earth and was just grabbed into orbit, then we would have been able to, we would have found something completely different. And we didn't find that. We have a match. It didn't form separately, or it would have had the same fraction of iron cores. So if it had been formed at the same time as the Earth out of the disk of material going around the sun, then we would have had a situation where it would have basically been a mini clone of the Earth with an iron core. So it matches the outer skin of the Earth, so somehow it was split off from Earth's outer layers at some point in the past. So this then takes us into some theories as to how that might have happened. The Big Splat, great name. The Earth was formed about 4.5 billion years ago, as I said before, and maybe was hit by another small planet. This is the Big Splat theory, about 4 billion years ago. And that would have caused a huge explosion. But at a glancing angle would have meant that the core of the Earth wasn't disturbed. So that would then mean that the material being blasted off the young Earth would have been from the outer layers only. And there's a little animation here which is trying to illustrate that. And you can see that you have a lot of molten rock being blasted up into space. The Earth would have to reform, and then the moon would have formed out of the stuff that was left floating around. Some theories suggest that actually 2 moons were formed, but we'll come to that again in a minute. The impact would have ripped the outer layers of the Earth away. It would have thrown the remains into orbit. The iron core would have been left intact. The moon would have been formed from the debris in orbit, and that explains why the moon is made of Earth's skin and not out of the core. A way in which this could have happened is explained by the Theia theory. Theia theory works on the basis that we had a situation potentially with the sun, the center of the solar system. We had the Earth in orbit around the sun. This is slide 1. And then at a point called the Lagrange point 5, a moon or another body would have been forming. And the Lagrange points 5 and 4 here are 2 points in the orbit where other objects can stay stably, even though they're in the same orbit as your prime object, the Earth. But they can only stay in a stable orbit as long as they remain relatively small. The theory goes that over a period of time, the small object would have built up additional mass through picking up debris out of the orbit to the point where it would have become unstable. And then finally, it would have wobbled away from its Lagrange point and come into a collision point. And that's how the moon could have been formed. So that's a theory which is worth exploring. This gives you a little graphic showing that same journey. I like my little animations. But you can see the theory here as you start on the Lagrange point, you go unstable, the unstable moon wanders around the orbit until it collides with the Earth and knocks off the material which creates the moon. And this series of images here shows the same story, but with one extra factor, which is another interesting part, is that potentially this impact could also have been the reason why we've ended up with the Earth's tilt. Most of the planets in the solar system actually are relatively upright. Excuse me. We have a 23-degree tilt, which has actually been very helpful because it gives us the seasons and a whole bunch of other things. and it's tilted our magnetic field as well. So that tilt could have been induced by this impact when it happened. So overall, this looks like the most likely theory. However, there are other theories, and there are theories that there were two moons which were created, and that those two moons subsequently collided, which explains why the moon itself is lopsided, that the skin on the outside, the side we don't see very often, is thicker than the skin on the inside. That could have been explained by there being a subsequent collision of two moons which have been created through this process. So there are things we don't know, but what we do know is that the moon is made of Earth stuff, and it was mostly made out of something as a result of a collision in the early evolution of the universe, of the solar system. And at that point, we said we'd have a quick break. So it's time to go and get a cup of tea, if you like. I'll stop for about 3 minutes, if that's okay, and I'll watch for people to come back in. I have unmuted everybody, by the way, so watch your P's and Q's.
How much to Amarillo Village? I want the real price, sir, not some number you can't help me out. 900 rupees. Yeah. And then after it left off the moment, what happened? Occupational hazard around Diwali, I'm afraid.
And we'll move on to our next destination. We're going to do a bit of canal time now. We're still in the inner solar system. Moving on, though, from the Earth, we'll move out to Mars. And first, a little bit of history about the work to discover Mars, what was going on. Start off with Tycho Brahe, or Brahe. I mean, different people pronounce it in different ways, and I'm sure I pronounced it incorrectly. But a famous Danish astronomer, were renowned for various different things, one of which was that as a 20-year-old, he fought a fellow student in a duel over who was the better mathematician, and as a result, he lost a large chunk of his nose. And for the rest of his life, he had a metal prosthetic nose to cover his disfigurement, which is an interesting claim to fame. But he was a brilliant astronomer, and even back in 1576, he worked out how to predict the position of Mars very accurately. So most people at that stage in astronomy were looking at objects and trying to see things which were unusual on a sort of a case-by-case basis. What Brahe did differently was he tracked things. He would do a series of observations of a particular object, and from that make deductions. So, for instance, he identified a comet because he saw the comet, but then he tracked it, and he figured out that the comet was actually moving against the background of the stars and relative to the planets. So he knew it was a different sort of object, was able to tell people that it was that. He also saw a supernova. And the supernova, he recognized that it wasn't moving relative to the background of the stars. It was a star which had gone supernova. So he was able to draw some really good conclusions from what he was seeing. And he was doing this in a way which other people hadn't actually worked out. He was so good that King Frederick II sought to keep him in Denmark by basically bribing him. I'll just try and get the information. They offered him his own island and financial support. And this was successful. It was a good bribe. And so he built an enormous observatory, and he did lots and lots and lots of observations. He was working away from the old heliocentric version of the understanding of the solar system, but he didn't go quite all the way. The world wasn't quite ready enough for that. So he ended up with a situation where all the other planets went around the sun, but the sun still went around the Earth. which made some of the orbits of the sun, of the planets, as you watch them, rather difficult to work out because there were funny little loops and reversals which he couldn't explain. However, he was very good, and by his tracking of the position of Mars, he was able to then produce predictions of where Mars would be to within about 1/100 of a degree. And this is before the days of telescopes. It's pretty impressive. Now, a pupil, or an associate of Brahe was Kepler. And Kepler knew about Brahe, knew about his observations. He was very, very keen to get hold of this data. And so he contacted Tycho and said, I'd like to have a look at your data. And Tycho said, well, no, you can't have the data. You can come and work for me, though, be my assistant. And so he did that. But then he didn't actually let him have any of the data. He just did works on various different things. He did do some work based on the observational data, though, and Kepler is famous for his equations of planetary motion. And you'll see the illustration on the screen there, which is just showing one of the main things here, which is just showing that we have an elliptical orbit, which Kepler figured out. He said that the planets were not going in circles, they were going in ellipses. And using this mechanism where you've got the sun at the center of, or not the sun within the ellipse and a planet going around the ellipse, this is a very simplified version, but it says if you have these triangles which are drawn, the area of the triangles is always the same, while for the distance traveled by the planet. So if you have an area 1, the planet will travel from A to B in a certain amount of time. Whereas when you get out to here, where the area is 3, same amount of area, the planet will take the same time to travel from E to F as it took from travel from A to B. And what that's telling you is that a planet is moving more quickly when it's in the closer part of its orbit and more slowly when it's in the outer part of its orbit. And it allows you to calculate very well where a planet will be in its orbit at any given time. And he came up with these laws published in the Astronomia, Nova, which was his great publication. Kepler worked for Brahe for some time. Brahe eventually died, and at that point Kepler effectively stole some of his data and was able to then really move on and develop and publish his findings. So, moving on again, we have our famous Galileo Galilei, the first person to look at the stars, or do astronomy through a telescope. And he made one that could magnify 20 times. I don't know how accurate that picture is as a picture of it, but it may not be a bad one. And he drew the first ever map of Mars. And it's, you may think that looks a bit scratchy, but if you look at the map and look at Mars, you can see that it's actually not a bad effort. It's a pretty good attempt through a relatively limited telescope, and that's as good a view as, well, certainly a better view than I typically get through my telescope. So a major step forward for observation. And then we move on into the 1870s, and Schiaparelli, Italian astronomer, who quite innocently used the term canali, which was from the Italian, describing the streaks on the surface of Mars. It was just like lines. However, it was mistranslated as canals, and the world went mad. And the idea was we now had this world where there were canals being dug because it was a dying world and all the water was at the poles, and they needed to this advanced civilization was digging canals to try to get the water from the poles to the tropics so they could actually continue to grow. So it was quite a fun thing. Lots and lots of interesting images coming out. We were channeling water from the polar caps to the Martian cities, but it wasn't true. The straight lines are not there. And when you look at images of Mars now, there's no sign of any canals. This is just a real map. Various different theories exist as to what they were actually seeing, whether it was aberrations caused by the relatively primitive telescopes that were being used. Maybe it was just a reflection of the back of their own eyeballs, and it looks very similar to some of the pictures you see if you look at these views that the opticians take of the back of your eye to show you how badly in shape your eyes are. So it wasn't true. However, it is just now a dry desert now, and this is one of the many pictures we now have of Mars showing the excuse me, the rusty landscape. But it could have been very different. And if you look at this flattened out image of Mars, you'll see that we've got a northern area which is very flat. There's very few craters in this northern area, whereas the southern area there are lots and lots and lots of craters. And the colour on this picture, once again a false colour, is to give you an understanding of the altitude, the height of the image. So the blues are low-lying areas. The oranges and the reds are mountainous areas, they're high-lying areas. What we're seeing here is that the high-lying areas are very old. They've got lots and lots of impact craters, and there's nothing has happened to change that over time. Whereas the blue area, there's very few impact craters. And the suggestion is that that was actually an area which was ocean, and there's water on Mars in big ways. And he gives you a picture of what it might have looked like, that same area, with this large ocean, lots and lots of water. Lost because Mars was too small to hold on to it. The atmosphere and the magnetic field were not sufficient to keep the impact of the solar radiation away, which resulted in the water being basically disintegrated and driven off the planet. And so now there's no surface water on Mars, as far as we can see. There may be some water, very residual water below the surface, and various different things are searching for that. Is it Mars? I've forgotten the name of the mission now, but the mission that's currently using a mole to drill into the surface is looking to see if it can find any traces by going a bit further down under the surface. So Mars could well have had water in the past. What it definitely has, though, is two moons. That's Phobos and Deimos, Fear and Terror. Now, these are interesting moons because they are not moons formed in the same way as we see our own moon. These are most likely captured asteroids. You can see they're not very round, and Phobos is actually going the wrong way round and is spiraling in towards a crash. So they're very, very different from the moons of the Earth, or the moon of the Earth, sorry. Phobos means fear, and Deimos means panic. They are the names of the horses that pulled the chariot of the god of war, which was Ares, which is the Greek name for the Roman god Mars. So they've been named in conjunction with the name of the planet. And an amazing prediction, which happened 150 years before the discovery of those moons. The moons were discovered in 1877. Back in 1726, Jonathan Swift in Gulliver's Travels wrote this passage. And he was talking about Mars. Mars was well known, but at that point, the moons hadn't been discovered. And the passage says, they have likewise discovered two lesser stars or satellites which revolve around Mars, whereof the innermost is distant from the center of the primary planet exactly 3 of his diameters, and the outermost 5, and the former revolves in the space of 10 hours, and the latter in 21.5. Now, the actual orbits of Phobos and Deimos are 1.5 and 3.5 diameters, so not the 3 and the 5. And the actual periods of the rotations are 7.5 and 30, not 10 and 21. But it's still a pretty amazing prediction, isn't it? So there's lots of thoughts about how this could have occurred. Many conspiracy theories can easily be spawned from this. But the fact that Jonathan Swift was able to put into Gulliver's Travels the fact that he believed Mars had 2 moons, maybe it was a lucky guess. Maybe he'd seen that Mercury had none, and Venus had none, and Earth had 1, and Jupiter certainly had 4. At that point, they'd have known 4. They wouldn't have found. So maybe it's just logical mathematical regression. You thought Mars must have 2, but a lucky guess, but an interesting prediction nonetheless. So that's a prediction back to our questions from the very beginning about what Jonathan Swift predicted. So let's carry on now to the outer solar system, and we'll talk about some of the gas giants. We have 4 gas giant planets, 2 of which are usually called the ice giant planets, which are the Uranus and Neptune on the far end. But we'll start off by visiting Jupiter. Excuse me again. So Jupiter is the largest planet of all. It's twice as massive as all of the other planets combined, which is just ridiculously big. And it's why when you have Jupiter visible in the sky, it is such a large, such a bright object. It is currently visible in the morning sky. I haven't got myself out of bed yet to see it, but Jupiter and Saturn are both visible. And this image is not a true image, it's just to represent the size of Jupiter's moons in comparison to Jupiter, so it's all to the same scale. And what you can see is Jupiter in the red spot, and the red spot is big enough to eat the Earth about 3 times over. I think it's about 1 diameter of Earth that way and 2 diameters of Earth that way. so you could actually get Earth into there quite easily. And the 4 planets there, sorry, the 4 moons are Io at the top, Europa, Ganymede, and Callisto. And these are the 4 Galilean moons. So they were discovered by Galileo Galilei with his telescope. And you can see them quite easily with a pair of binoculars or a telescope now. And it's a very impressive sight. And you often see the 4 moons aligned, sometimes 2 on each side, sometimes all 4 on one side. But they move very quickly. Everything's moving quite fast on Jupiter. The planet itself rotates every 10 hours. The orbits of the moons are quite rapid, and if you get any of the monthly astronomy magazines, they usually give you a little chart showing you the position of the moons on any given day, and it's quite fun to actually track them around. You'll notice down at the bottom here there are a lot of moons. There's 75 additional moons, so 79 moons in total, and some of those moons are still awaiting confirmation. So this is one of the numbers which changes rather frequently when you're doing talks like this, is that more moons are being discovered all the time. I want to move on to another factor, and something which people don't know so much about on Jupiter is Jupiter's rings. This is the 3rd ring system which was discovered. Saturn obviously was discovered first, and Uranus was also picked up quite early. But the Jupiter's rings were first observed by Voyager in 1979, Voyager 1. They're very, very faint. They're not, you can't see them through a terrestrial telescope. They have been obviously imaged by Voyager, and they were have been imaged by Hubble. But I think from Earth, they are so nebulous, they are so fine that you really can't see very much. They consist of a halo, which is the biggest part of the rings, the most substantial ring, and then a series of very, very fine gossamer rings, which are really only a matter of meters thick, very, very, very thin, and associated with a series of moons. So we have the moon Thebe, and all the material in this green bit of ring is material being shed by Thebe, and the moon Amalthea. And that's responsible for all of this yellow material. So we can see that that's going on. Now, in many ring and moon systems, we find shepherd moons who are actually clearing material out of the rings. What I've read about this is that it seems that in this case, the moons are actually shedding material into the rings. I'm not 100% certain about the veracity of that. However, what I can say is there is a fact that there is a ring system. It's much more nebulous than the ring systems in other places, but it's a ring system nonetheless. I'm not going to spend a lot of time on Jupiter, because I think we did a lot of talking on Jupiter and the ice planets yesterday in one of the other talks. So I'll move on to Saturn. And this is a slightly trick picture. It's a family portrait. It has very little of Saturn in it. The only piece of Saturn in this picture is actually the rings here. Everything else is a moon. There's 5 moons here. There's 1, 2, 3, 4, and this is a moon. This is not the center of Saturn. And it's an image taken by Cassini, as it captured these in a single frame with its narrow angle camera. And I just thought it was a rather nice picture. The moons are Janus over here, which is 179 kilometers across. Pandora is this tiny little one there. Just beyond the thin ring. There's the very bright Enceladus. Enceladus has got a very bright reflective side, which is a large moon as well, 500 kilometers across. Saturn's second largest moon, Rhea, is this one here. So this is a large moon, 1,500 kilometers across. And then finally we have the smaller moon, Mimas, which is only 400 kilometers across. Get my thing, there it is, just tucked behind Rhea. And this was taken by Cassini at a distance of about 684,000 miles from Rhea. And it was just an impressive picture. So some of the statistics about Saturn, it's about 900 million miles from the sun, so 10 times as far as Earth is from the sun. Therefore, it only gets 1/100th of the light, which makes it even more impressive that it can be such a bright object. When you look at Saturn, you see it quite clearly in the sky. Orbits 29 years and spins similar to Jupiter. One rotation, one Saturnian day is about 10 hours, so it's going around pretty quickly. And as with all the gas giants, because it's a gas giant, the actual speed of the material making up the planet is not constant across the whole body of the planet. So some parts of it are spinning faster and some parts of it are spinning slower. It's cold because it's further out from the sun, so minus 280. I don't know why I've got Fahrenheit there, but there we go. And the atmosphere is hydrogen and helium, so made up of the prime gases from the rest of the solar system and the universe. But talking about moons, it has 82 moons, and a whole bunch of these were only discovered last year. I'll just flick through my notes on this one to give you the proper detail of it. It's actually in October 2019 that some researchers announced they'd found 20 new moons, which took the total up to the 82. And that meant it overtook Jupiter, which only has 79. And these moons are actually in a number of different orbits. You can see we've got Saturn in the middle here. We have a lot of moons going around in this red orbit. You can see the little arrows on the direction there. And then we have one or two which are going the other way around in the same area, but going the opposite direction. And then a few more which are going in a completely different orientation in that dot. And these have all been named by different things. So this is the Inuit group. The red ones are the Norse group, and the green ones are the Gallic group. There are so many moons now, they're actually clustered into groups. And we've missed it now, I'm afraid, but there was a competition to name the new moons, and you could have entered your suggestions, but you had to stay with the conventions. So any moons you identified, you'd had to have called them either a Gallic name, an Inuit name, or a Norse name, after the Norse gods or the Inuit gods in each case. So new moons are Saturn. So Saturn has taken the lead now in the number of moons. And this gives you an illustration of the sizes of moons. And it is quite an interesting setup. You can see Jupiter, we have the 4 very large Galilean moons. Excuse me. Saturn, we have Titan, which is a very large moon. It's one of the big boys of the solar system. But then we have many, very small moons, and they're obviously not all listed here. What I have done is I went onto the NASA site earlier on today, pulled up this list. This tells you the total current tally of moons in the solar system. So we're up now to possible 214 moons, and that includes the moons around all of the 8 main planets, also moons around the dwarf planets. And it's an interesting fact is that there's only 3 objects on that list who don't have any moons. And that's Mercury, Venus, and Ceres. When I did this talk about 6 months ago, Makemake had nothing, but now it has 1 provisional moon. So we'll see what happens next. Moving out to Uranus, we have another of the gas giants, but this one is now in the ice giant category. Discovered by William Herschel, and there's a picture of William Herschel with his sister Caroline working away, discovering it. Caroline did a lot of the work and was probably an equal astronomer to William. Of course, William got the credit. William Herschel discovered it and then tried to name the planet for King George. He was going to name it Georgium Sidus. And unfortunately for him, that was turned down. It was named Uranus after the Greek god of the sky. But he was working very hard to get into the good books of King George, and that worked. He was appointed by King George and was commissioned to make some telescopes. And this is one of the telescopes that was made. I think these are 10-foot telescopes, and I think he made 10 of them. And this one's actually in the Whipple Museum in Cambridge, so you can go and see a Herschel telescope for yourself. A very impressive piece of kit. He started off with 10-foot long ones, went to 20 foot, and then went to 40 foot. The 20 foot was the one he did most of his good work with. The 40 foot was just unwieldy and didn't really work very well. It would work very well, but it was just very difficult to use. Another interesting factor about Uranus is that it actually rolls around on its side. And we talked about Mercury having an impact which caused it to lose its outer body. We talked about Earth having an impact which caused a bit of a tilt. Suggestion is that Uranus had a big impact which actually put it on its side very early in the formation of the universe. And so you can see that it effectively rolls around in its orbit. And it goes around around the sun, in 84 years. It therefore has 4 seasons, which are each 21 years each long. But because it's rolling round on its side, the main part of its exposure to the sun is actually onto its poles for half the year in one direction and half in the other direction. It means one pole is in darkness for 42 years, and then the other pole is in darkness for 42 years. And we have a very strange heat distribution. There's lots of things we don't know about Uranus, basically. It's a very unusual place. This illustrates the orientation for the poles, and this is a period, this is a simulation over half of an orbit. So it runs from the summer solstice through to the northern summer solstice, and shows you what you would see from the Earth view, which is effectively from the sun view. So you're swinging around from one pole to the other pole as you proceed over that period of time. And we have another ring system, and I won't spend a lot of time on it, but we have a very structured ring system here. And in this case, we also do have the shepherd ring set up. And you can see that we have, in each ring, you have a set of moons, and the moons are often clearing the gap to make the space between the rings. The other thing to note about Uranus is that you'll see that the names of the moons are actually all Shakespearean or other literary characters, and this is an unusual setup. Every other planet, things have been named usually after Greek or Roman gods. In the case of Uranus, the decision was made to name the moons after mostly Shakespearean characters, so you recognize the characters there. So moving out one more, the last planet of the journey, we go to Neptune, the windy planet. It's the fourth largest planet, but it's the place where we have the most extreme winds, and we also have some of the coldest temperatures. It has a very active atmosphere with visible weather patterns. You can see on this image some clouds there, and there was, at the time of the Voyager 2's flyby in '89, a great dark spot comparable to the great red spot on Jupiter. So you have these long-standing, very, very large storms. But on on Neptune, the winds can get as high as 1,300 miles an hour, 2,000 kilometers an hour. Very, very windy, and it's also, because it's so far from the sun, it's one of the coldest places in the solar system. Temperatures at the cloud tops will be about 55 Kelvin, and remember that Kelvin starts at minus 273 centigrade, so that makes it about minus 220 centigrade at the cloud tops. At the planet's center, you get up to some more, planetary numbers. You get to about 5,000 degrees centigrade in the core of the planet. And that's residual heat left over from when the planet was formed, potentially being retained to a certain extent, partly by the size of the planet, partly by the gravitational pressure causing heat to be generated in the center, maybe by some sort of radioactive generation as well, as we know that happens on Earth. The atmosphere is composed primarily of hydrogen and helium, with some traces of hydrocarbons and maybe nitrogen, but it also contains a high proportion of ices, such as water, ammonia, and methane. In the center of it, like Uranus, it's primarily composed of ices and rocks, and that's why you've got Uranus and Neptune being called the ice giants, as opposed to the situation for Saturn and Jupiter. And you'll be surprised to see yet more rings, 5 principal rings. These were discovered in 1984. They were imaged by Voyager 2 in '89. They are, once again, very dark, very difficult to see. And they have some interesting features. You can see there's a number of different rings. We've got a combination here of orbits, of moons, and we have the rings themselves. And we also have this situation where we have these 5 arcs, which have been discovered here. I'll just go out the names of those because they're quite interesting. It's named after some French terms. We have égalité, liberté, and fraternité. And there's actually 2 égalité ones. So you have fraternity, égalité 1, égalité 2, liberté, and then they obviously ran out of French terms. So the 5th one's called courage. And these 5 little arcs here are remarkably stable. I know we haven't seen them and known them for very long, but in the time that we've seen them, they have stayed where they are. And we think that stability it could be to do with the resonant interaction between the Adams ring and its inner shepherd moon, Galatea. So there's the Adams ring, and there's Galatea. So Galatea will be having some sort of an impact on maintaining the stability of that. So having moved from a position relatively recently when we saw Saturn and Saturn's rings as being a novelty and an unusual thing, we've now got a situation where we've discovered rings around all 4 of the external giant gas planets, which is something, well, certainly wasn't in the textbooks when I was growing up. So. And then finally, we're moving out to beyond Neptune and the Kuiper Belt. You can see in this little diagram here, we have Neptune's orbit here. And Neptune has an influence on elements of the solar system which are beyond, and they're typically out in the Kuiper Belt here. The Kuiper Belt consists of lots and lots of small objects, but they are either unstable and moving around, or they stay in relatively stable orbits. And the stable orbits are driven by being in resonance with Neptune. So I take the orbit here, which is where Pluto sits. The orbit relationship between Pluto's orbit and Neptune's orbit is 2 to 3. So for every 2 orbits that Pluto does, Neptune does 3. And that means these stay stable. And even though we have a strange situation that Pluto actually sometimes is inside Neptune's orbit and sometimes outside, because its overall length is what it is, it takes longer to go around, and therefore it's going to take 2 orbits while Neptune does 3. And that means that they stay safely, not crashing together, and they maintain those positions. So there's quite a few objects in Pluto's orbit. And then there are other things out in these other resonant areas here in this whole of this Kuiper Belt area. So it's an area which hasn't been explored very much, but we have actually got the mission out there. So we have the New Frontier mission, which you may have heard of. This is a quick diagram of its timeline. It started off obviously with us in the middle. It explored, it was launched in 2006, went to Jupiter 2007, got to the Pluto system in 2015, and it's currently out in the Kuiper Belt, and you've probably seen the pictures of it visiting Ultima Thule, which has now been renamed Arakoth, the snowman, as it was called. These are images showing what's now being worked out about it. We were not quite sure what it was all about. They now think that these areas, rather than being contact areas, I thought this bit here was probably where something else had hit it. They believe it's just one of the building blocks, and each of these areas is a different piece of material which has been brought together to make the structure. So there's lots of research still going on into this area. And of course, New Horizons is still flying out beyond this, the orbits of Ultima Thule. And there is enough fuel on board for it to be redirected to something else. I'm not sure if a decision's been made yet, but I look forward to hearing more if and when that happens. So Ultima Thule is heading off, continuing on. We're out at this green place here. It's taken it since 2006 to get that far, so it's 14 years on its journey, but still going strong. So I think we've reached the end of our time. We have a little break just about right. So the 6 fascinating facts about our solar system. Who can remember what those questions were? We started off with Mercury, and there was something about Mercury's core, and the fascinating fact was that Mercury's iron core is bigger than the Earth's, and in fact it is the biggest iron core in the solar system. We talked about how Mercury was possibly impacted from being a larger planet, just to agree at that piece. We then talked about Venus, and we said that Venus is actually, it's the hottest planet because of that greenhouse gas, and it has a surface pressure that can crush a Seawolf-class nuclear submarine. Not a phrase you'd expect to see in an astronomy lecture usually, I have to say. And then the next question was, what is the moon made of? And I had various questions or various suggestions about green cheese, but we said it's made of Earth stuff. It sounds a bit boring, but it means we know more about it. We know how it's been made. We think we do anyway. We know it's definitely something which was made out of Earth's material. It's not something that's been captured from the outer solar system. It's not something which was made at the same time as Earth. So interesting facts have been thought about it. Now, the next stop was Mars, and we talked about the predictions made by Jonathan Swift, who talked about Mars's moons, Phobos and Deimos, 150 years before they were discovered. So a whole feast of conspiracy theory could be met there. We then went to the giant gas planets, and as we've just been saying, all the giant planets have rings. And I certainly didn't know that when I was learning my initial astronomy, and I think a lot of it is very recent discoveries. And then finally, we talked about moons, and the latest count from the NASA table was there are 214 moons in the solar system. And Saturn is currently in the lead, but I put so far because I wouldn't be at all surprised if somebody comes up with some more information. There are studies going on now looking for planet 9 still. And one of the reasons why those extra Saturn moons were found was because they were looking for planet 9 and happened to be looking past Saturn at the time and spotted the extra moons. So we're still finding out what we don't know. And I think we'll carry on doing that. Things change all the time. And that's the end of the talk for tonight. Thank you very much for joining in. Happy Easter, a little bit late.